Welcome to the 34th lecture of combinatorics. So, in the last class we discussed about partition numbers P of n. It counts the number of partitions for a given positive integer n. Number of partitions means how many ways we can express it as a sum of positive integers, right, where the order does not matter. We does not care about how we order the summons. So, then after figuring out the generating function for the sequence P0 of n, P1 sorry P of 0, P of 1, P of 2, etc. So, we went ahead to study some special kind of partitions in the sense that where we impose some extra conditions. We are talking about partitions of a certain type. The first special type of partition we studied was where the number of summons were equal to k, exactly equal to k. So, definitely if you want to get P of n, we just have to add up the number of partitions for where the number of summons is equal to 1, number of summons equal to 2, number of summons equal to 3, number of summons equal to n. Therefore, it makes sense to study this partition of case, this special type of partition. And then we saw some recurrence relation which is valid for those partition numbers pk of n, right. We see involving right, considering this as a family of sequences pk of n, for each k there is a one sequence, and then using this pk of n can be expressed in terms of smaller n, smaller k, right. That is what we discussed in the last class. Now, we will just get some crude estimates for pk of n. So, in terms of n and k. So, this is the next one. So, we are going to show now a lower bound and upper bound, right. This is, so first we will look at the lower bound. Pk of n is at least 1 by k factorial into n minus 1 choose k minus 1. Greater than or equal to k, sorry, 1 by k factorial n minus 1 choose k minus 1. So, this we can always write like k factorial into pk of n is greater than or equal to n minus 1 choose k minus 1. This comes from the fact that pk of n is the number of solutions for this equation, namely x1 plus x2 plus x3 plus xk equal to n, where the order does not matter. That means, to make sure that the order does not, by changing the order we will get a different solution. We also put the condition that this is greater than or equal to xk, and everything has to be at least 1. That is important, because we want exactly k parts, because if you put one of them 0, then we will get less than k parts only, right. So, but on the other hand, we told that there was this old equation we studied, y1 plus y2 plus yk is equal to n, and without this condition we just have yi. So, the only condition we have is each yi greater than or equal to 1, not 0, 1, right. So, what is the difference between these two? So, here also, so the only difference is that here we have to have x1 strictly bigger than x2 strictly greater than. So, what we can notice is, if we get one solution for x1, x2, xk, etc., then we can try to permute that solution. For instance, if x1 is assigned a value a and x2 is assigned a value b and so on. So, we can try to give a to here, b to here, right. So, permute the values assigned to x1, x2, x3, xk to all possible ways. Definitely it can be done in k factorial ways, right. So, what is assigned to x1 can as well be assigned to x2 or x3 or sk, and what is assigned to x2 can be assigned to any of the remaining k minus 1 possibilities and so on, right. So, actually there are k factorial maximum possible number of permutations that we can get. Each of them may give a solution for the second problem, right, because there the order is not important, second problem, right. But you note that see, when you permute, so if there were repetitions here x1, x2, x3 etc. were all equal, so then they won't be k factorial permutations, they will be k factorial divided by some other something. That something will be the, say for instance, if a certain value is repeating k1 times, then k1 factorial will come in the denominator. We have seen it several times. So, but the maximum possible is when they are all distinct, and that is k factorial. So, that means from a solution for the first equality satisfying this condition, we can get at most k factorial possibilities for the second one. That covers all the possible solutions for the second one. In other words, if you get a solution for the second one, so we can in fact see it as coming from a solution for the first one by some permutation of it, because what you do is we will rearrange those solutions such that y1 get the maximum, y2 get the second maximum and so on, right. So, that will be a solution for the first equation, right. But then one solution for the first equation give rise to many solutions for the second one, but maximum k factorial. That is why k factorial into pk of n is greater than or equal to the number of solutions for the second one. We claim that the number of solutions for the second one is n minus 1 choose k minus 1. Why is it so? Because the second one is y1 plus yk equal to n, but here we have the condition that yi is greater than or equal to 1. So, now we can convert it to another system, z1 plus zk equal to n minus k by defining zi equal to yi minus 1. We just reduce 1 from each of them, because each yi is greater than or equal to 1. Now, zi will be greater than or equal to 0, is not it, because that is what will happen by doing like that, because each yi was greater than or equal to 0, you reduce 1 from each yi and get zi. So, zi will remain greater than or equal to 0. So, this is a very familiar one. We know the solution for this thing is n minus k plus k minus 1, choose n minus k, or maybe we can also set k minus 1 here, that is all same, right. So, this cancels. So, that is n minus 1 choose k minus 1, right. So, here I am saying that you say earlier we used to write n minus k here, but that does not make any difference because of the symmetry property of the combinatorial coefficients, right. Whether I write n minus k here or k minus 1 here, it is the same thing, right, because n minus 1 minus n minus k is actually k minus 1, right. So, this is where this is coming from, right. So, you get this thing. And now for the upper bound, the upper bound is 1 by k factorial into n plus k into k minus 1 by 2 minus 1 choose k minus 1, right. How do you do this? So, we want to show that pk of n is less than or equal to 1 by k factorial into n plus k into k minus 1 by 2 minus 1 choose k minus 1. So, or in other words, we can say we want to prove that k factorial into pk of n is less than or equal to this. Now, we will use the same argument as before. You remember the this pk of n correspond to the solutions of this one, x1 plus x2 plus xk equal to n, with this x1 greater than equal to xk greater than equal to 1. This was the condition for this thing. Now, given any solution for this thing, we can generate at most k factorial solutions from this thing, right, by rotating solution for n. But the only problem is there can be some. So suppose they were actually k factorial into pk of n solutions for this stuff, then we can say that the number of solutions for this one, when we drop this condition, xk minus xk is great, so all this xi greater than equal to 1, this condition I retain, but the other condition that x1 has to be the biggest, x2 has to be the next biggest, that condition we drop. That means we can we can have different orders for the values can be assigned to different. For instance, whatever is assigned to the x1 first can be assigned to x2 later, and so on, and get a different solution. If that is the situation, then we could have written, say, the number of solutions for this thing, namely n minus 1 choose k minus 1 as an upper bound. We cannot do it because actually we may not get k factorial into pk minus 1 different solutions. That many may not be there, because many times the solutions for corresponding to pk of n may have repetitions, so k factorial may not occur. So one thing we can try is to make these values distinct. How do we do it, right? So this is the way we will do a transformation. We will define y1 plus y2 plus yk equal to something here, n plus something here. How do I do it? So what I do is yi will be defined as xi plus k minus I. So for instance, y1 will be equal to x1 plus k, right, y2 will be x2 plus, sorry, k minus 1, y2 will be x2 plus k minus 2, and so on, and yk will be equal to xk plus k minus k, namely xk itself, right. So we try this conversion, right. So we convert each xi into yi by defining like this, xi plus k minus I. Now you see the total we are adding to the, so see x1 we are getting adding k minus 1, x2 we are adding k minus 2, finally yk minus 1 we are adding 1, and here we are adding only 0. So how much we are adding? So this is k into k minus 1 by 2, because there are the first term 1, last term k minus 1, and the number of terms k minus 1. So the k into k minus 1 by 2 is the total we are adding here. So we just write like this. So this is a conversion. So we still have y1 greater than equal to y2 greater than equal to this thing, but then any solution for this thing, this first equation, will give a solution to this equation where each value is distinct. Each value is distinct. Now each of the solutions give k factorial permutations of the solutions, right. We can reassign those values, keeping the values same. We can assign to y1, y2, yk in all possible ways. There are k factorial permutations possible for the coming from each such solution, right. So, therefore, from this thing, so see, of course the claim is that we get y1, y2, yk all distinct after doing this transformation. So, if they really happens to be distinct, then this k factorial into pk into n will be the total number of solutions for this equation, right, for the original one, total number of solutions with distinct values, right, because these are all distinct. Sorry, what we say that corresponding to each solution of this thing, we will actually get a distinct solution for this thing, and that can be permuted in all possible ways. That all corresponds to the solution for the equation of this sort, y1 plus, sorry, yeah, so y1 plus y2 plus yk is equal to n into n plus k into k minus 1 by 2, where each yi has to be greater than or equal to 1. The condition that y1 has to be the biggest, y2 has to be the second biggest, that is removed, right. Once again I am saying that you find a solution for this thing. Now make this transformation. Now you get the solution for this equation, where y1 is biggest, y2 is second biggest, yk is last, and so on. But and here they are adding up to n plus k into k minus 1 by 2. But now all the values for y1, y2, yk are distinct. Now you drop, suppose you drop the restriction that y1 has to be the biggest, y2 has to be the second biggest and all, then we will get k factorial times this number of solutions, which are the solutions for the resulting equation, namely this equation, right. See, here there can be more solutions because there is no restriction that their solution has to be distinct or something, but then these are all solutions for this thing, namely this k factorial into pk of n possible solutions are all solutions for this last equality. And we know this number is actually so has to be less than or equal to total number of solutions for this thing, which is actually n plus k into k minus 1 by 2 minus 1, choose k minus 1, right, because there are k things. This takes the role of n here, right, n. So, n minus 1, choose k minus 1, right, because we have this extra condition says y is greater than or equal to 1, that was always n minus 1, choose k minus 1, but n is replaced by n plus k into k minus 1 by 2 here minus 1. So, this will come. The only thing we have to now establish is that these are all distinct, right. Why are they distinct? Because we defined yi is equal to xi plus k minus I. Suppose this was equal to some yj, namely xj plus k minus j. So, without loss of generality, we can assume that this xi, this I was smaller than j, that means this xi is bigger than xj. Now, when you take xi plus k minus I, suppose this is equal xj plus k minus j. So, that is xi minus xj equal to I minus j, but I is smaller than j. So, this is a negative number, but the xi is bigger than xj, this is a positive number, right, positive number. Now, positive or 0 does not matter, but this is strictly a negative number. So, therefore, this is wrong, contradiction here. So, therefore, yi and yj can never be equal, they are distinct. So, from this thing whatever we are trying to prove follows, right. So, what we have got now is pk of n is less than or equal to n plus k into k minus 1 by 2 minus 1, choose k minus 1, and the lower bound was k factorial into lower bound was n minus 1, choose k minus 1, right. Now we can probably try to see how much is this. So this n minus 1 k minus 1 will look like n minus 1 into n minus 2 into, so k minus 1 terms, n minus 1 minus k minus 1 plus 1, right, divided by k minus 1 factorial. But yeah, and this k factorial I can take out, this is greater than less than equal to pk of n. So now see, suppose n is a very big number compared to k, that means k, you fix k, and as n tends to infinity and fixed k, right, then what will happen? See, we can say that these are all n minus 1, n minus 2, n minus 1 minus k minus 1 plus 1 and all, which is n minus k plus 1. So these are all about n, right, though some small difference is there. We can say approximately this is n to the power k minus 1, because there are k minus 1 terms in the numerator. See, this is approximate, we are assuming that n is very big compared to k, and is tending to infinity, k is fixed. So it is approximately n to the power k, here below it is k minus 1 factorial, k factorial. So this lower bound is like approximately n raised to k minus 1 by k factorial into n minus k factorial. Similarly, the upper bound pk of n is less than equal to 1 by k factorial into, right, n plus k into k minus 1 by 2 minus 1, choose k minus 1, right. So here you can see, starting from n plus k into k minus 1 by 2, we have k minus 1 terms written downward, that is a falling factorial starting from that n plus k. So because k is considered to be much smaller than n, we can just approximately each of them are n. So this is again 1 by k factorial into approximately n raised to k minus 1 above and k minus 1 factorial below, right. So we again get that above, so approximately both lower bounds and upper bound seems to be this. So we can write pk of n is approximately n raised to k minus 1 by k factorial into n minus k factorial, sorry, and k factorial into k minus 1 factorial for n tends, when n tends to infinity, and fixed k. Yeah, because this is because we are assuming that n is too large compared to k, right, k will not have much effect on this extra terms. So now up to now we were discussing one special kind of partitions, namely the partitions where the number of parts, number of summons is equal to k, fixed k, right, for a fixed k. Now we will consider a different kind of partition, namely when all parts are distinct. What do I mean by that? All parts are distinct. See, for instance, if we can take 10, so 10 equal to 10, this is a one summon partition. Anyway, there is nothing to discuss there because it is on all parts are distinct. Then for instance 10 can be written as 9 plus 1. Here all parts are distinct, 9 and 1. It can be written as 8 plus 2. All parts are distinct here. It can be written as 7 plus 3. All parts are distinct here. It can be written as 6 plus 4. All parts are distinct here. It can be written as 5 plus 5, but the parts are not distinct here, 5 and 5, right. So this is not a partition where all parts are distinct. So now, so this many, for instance, if you consider 3 summon partitions for 10, so 10 equal to say 8 plus 1 plus 1, but this is not allowed for us because all parts are not distinct here, because this 1 and 1 appears 2 times here, right. So therefore this is not, but on the other hand 7 plus 2 plus 1 is allowed, parts are distinct here. Now we are interested in what is PD of 10, namely the number of partitions of 10 where all parts are distinct, PD of n in general, right. So we before we won't estimate the value, but we would rather see what is the generating function for that. That's what our aim now, as of now, PD of n, right. So we have to worry what is PD of 0. As usual, we will assume that it is 1, because when we write down the generating function, it has to be 1, because we are taking it as the coefficient of x raised to 0, and that has to come as 1. So PD of 1, PD of 2, this sequence. So let us consider the generating function for this sequence, right. So that means I equal to 0 to infinity PD of I into x raised to I. This is the generating function. This generating function is actually, if you give some thought, is equal to pi of 1 plus x raised to I equal to 1 to infinity. Why is it so? Because the first term will allow us to select the number of ones, but only one. So this is 1 plus x. Earlier we used to write 1 plus x square plus x cube plus like this, an infinite series, a power series here. But that only meant that we are allowing to take 1 1 or 2 ones or 3 ones or whatever number of ones we want. But now we say we won't allow 2 ones or 3 ones or more ones, right. So we will just allow just 1 1 or 0 1, that's it, right. So 1 plus x is allowed. Similarly, next term will be 1 plus x square. What does it mean? We are allowing either 0 2 or 1 2, not more than that. Earlier we used to write there this one, right, x raised to 4, x raised to 6 and so on. That means and in general when you want to select k2s, we would just picking up this x raised to 2k from that, right. So but then we are not allowing all those things now, because we are allowing only 1 2 or no 2, right, because we are talking about distinct parts. No part should repeat, right. Similarly 1 plus x3, 1 plus x4, 1 3 will be allowed, 1 4 will be allowed, not more than that, right. So this is why this generating function is like this, okay. Yes, PD of I into x raised to I. Now the next thing, next type of partition we want to consider is this one, the PO of n. What is this? The partitions of n where all the parts are odd numbers. For instance, again 10, if you take 10 equal to 10, this is not a valid partition. Why? Because 10 is not an odd number. But 10 equal to 9 plus 1 is a valid partition, because both 9 and 1 are odd numbers. 8 plus 2 is not valid, because these are not odd numbers. 7 plus 2 plus 1 is not a valid partition, because 2 is an even number here, right. But on the other hand 7 plus 1 plus 1 plus 1 is valid, because these are all odd numbers, right. And similarly 5 plus 5 is allowed, because both are odd numbers, and so on, right. And similarly 10 equal to 1 plus 1 plus 1 plus 1, 10 ones, right, is a valid one, because they are all odd numbers. And the number of such partitions are called PD of 10, right, the number of odd partitions, sorry, PO of n, right, number of odd partitions of 10, right. So we are in general interested P of n. So, an interesting observation that can be made if you work with small examples. For instance, try with some numbers 1, 2, 3, 4 like that up to 10 we try and count, make a list of these values PD of n and PO of n, make a table, right. For each n you just list down what is this value, what is this value. You will see that both are same. Interestingly, we will define P of 0 is equal to 1 as usual, right. So, there also it will be equal. So, everywhere it will be equal is what we will see. But why is it so? We will give a proof of that, right. But before that, we will see how will I write a generating function for the sequence P of 0, P of 1, P of 2, this sequence, right. See, why am I writing the generating function? Because if I write down the generating function and somehow manipulate the generating function and show that this generating function is the same as the generating function I obtained for the other sequence, namely PD of 0, PD of this sequence, right. What does it mean? It would mean that both the sequences are same. For instance, PD of n will be equal to PO of n. This is what we can infer from that, right, in particular, right. This is what will come. So, now that is what our aim now. So, but then it is easy to find the generating function for this P of n sequence, because you are only allowed to take odd numbers, right. So, we should allow 1. So, this is okay, this is the first one, that means 1 is allowed, right, but 2 is not allowed to take. So, therefore, we will not add this stuff, because this was how many 2's are being selected, this was what this was determined. Anyway, we are not allowing this at all. So, we will not add it, but then 3 is allowed, next term is there, right, 1 plus x cube plus x raised to 6 plus x raised to 9 plus so on. And now this term 1 plus x raised to 4 plus x raised to 8 plus x raised to 12, this was counting how many 4's are being selected, but 4's are not allowed to be selected at all. So, we will not add that, but the next 5, yes, that is okay, 1 x raised to 5 plus x raised to 10 plus x raised to 15 plus this is okay. Like that we can write one term for each term. The intermediate terms which I am missing, namely the ones corresponding to the even terms, that because you remember this is exactly the same generating function for the P of n, but only thing is that we are skipping the intermediate, so the alternate ones, because the ones were written for 2, ones were written for terms written for 2, terms written for 4, terms written for 6 like that. But then this is what, this is 1 by x, this is 1 by x cube and 1 by x raised to 5 and so on, only odd numbers. This will be the generating function for say PO of x will be like this. Now, we will show that the generating function is the same as the generating function for PD of n. So, you remember the generating function for PD was this 1 plus x plus 1 plus x into 1 plus x square into 1 plus x cube into so on, right. But this 1 plus x is what? 1 plus x can be written as 1 minus x square by 1 minus x. Similarly, 1 plus x square, the second term, this can be written as 1 minus x raised to 4 by 1 minus x square, right. If you multiply this and this, you will get this 1 plus x square into 1 minus x square is 1 minus x raised to 4. Similarly, 1 plus x raised x cube can be written as 1 minus x raised to 6 by 1 minus x cube and so on. Now, we substitute here for this, maybe this 1 plus x, I will take this and substitute. So it's 1 minus x square by 1 minus x into, for this one we will substitute this, right. So 1 minus x raised to 4 by 1 minus x square, and this will come here 1 minus x raised to 6 by 1 minus x cube, and so on. Now you know, in the upper part we have 1 minus x square, 1 minus x raised to 4, 1 minus x raised to 6, all 1 minus x to the power an odd even number. Below we have everything 1 minus x, 1 minus x square, 1 minus x cube, 1 minus x raised to 4, and so on. So all those things which appeared in the numerator will cancel off from here like this, right. What will remain in the numerator will be 1, and below we will have 1 minus x, because even things will go away, 1 minus x cube, 1 minus x raised to 5, and so on, so on. If you remember, this is exactly this, right, and that is p of x. So what we have seen now is, just by manipulating the generating function, we have got PD of x is equal to PO of x, right, which means that the generating function for the sequence corresponding to the number of distinct partitions with distinct parts is the same as the generating function for the number of partitions with all odd parts. So it follows that PD of n is equal to PO of n. So very cute proof using generating functions, right. So that means, so what one should notice is that you want to make this observation, it's a little difficult because you have to play around with these partitions and then get a feel of these numbers, then only we can make such a conjecture. Even proof is different, so one should try to come up with a counting proof, straight proof without using the generating function. So then this cute simple technique using generating function one may be able to appreciate better. Now we will look at because now that we have talked about proving it in a different way without using generating functions, what are the other techniques available? So there is one technique by using a special type of diagrams called ferrous diagrams, right. What are these ferrous diagrams? In the partition literature this is very much used, and given a partition we can pictorially represent the partition like this. For instance, let us look at this partition of 10. 6 plus 2 plus 1 plus 1, right. So what we do is, we to represent 6, we in the first row we add 6 dots, and now the second part 2, we just add 2 dots in the second, and then we add just 1 dot, and then we add just 1 dot. This is a representation of this partition of 10. If you count the total number of dots, that is equal to 10, and the parts appear in the rows. So there are this many rows, therefore that is the first part, and you should know biggest part should come in the first row, second biggest should come in the second row, third biggest should come in the third row, and so on, right. This is the way the partition. You can take another example, for instance, say 8 equal to 5 plus 3 plus, or maybe 8 equal to 4 plus 9 equal to 4 plus 3 plus 2, right. Maybe again I write 10. 10 equal to 4 plus 3 plus 2 plus 1, just to get 4 rows. So the picture will be like this. So I will put 4 rows, 4 dots in the first row to correspond this 4, and then I put 3 rows in the next one, just below them, correct, in the proper way. It's starting from the leftmost, and then two dots in the third row, so to match this, and the one dot on this thing. Total number of dots is 10, and the parts of the partition appear in each rows. So this is called a ferrous diagram. So each possible partition of 10, we get a ferrous diagram. Now what is the conjugate of a ferrous diagram? So you could have, for instance, given this ferrous diagram, you could have say this ferrous diagram, let us say, you could have read it like this is the first row, this is the second row, this is the third row, this is the fourth row, fifth row, sixth row. This will correspond to, for instance, if I rearrange it, it will look like 4 dots here, 2 dots here, this one, right, this column will come here, and this third column, and then fourth, fifth, sixth. So this is actually 4 plus 2 plus 1 plus 1 plus 1 plus 1 is equal to 10. It's a different partition of 10, right. This is the conjugate of this partition, right. So it means instead of reading the rows, reading row wise, we read column wise, that's all, right. So we will it's obvious that we will get a partition, because it's the first column will be the longest possible, second column next longest, and so on, right. So this idea, so we can use this idea that by reading the columns, we will get another partition of the same number, and actually a ferrous diagram for another partition of the same number, we can prove something. So what do, for instance, look at this statement. The number of partitions of an integer into m summons is equal to the number of partitions of n into summons where m is the largest summand. So again, we were telling that we are considering different type of partitions. We still consider this thing. For instance, the first is familiar. Given n, we are talking about Pm of n. That means the number of partitions of n into m summons. Now we are saying this number is going to be equal to the number of partitions of n into summons where the largest summand equals m. Why is it so? Because if you consider a partition of n into m summands, it will look like this: some row, first row, then another second row, and then third row, then fourth row. So there will be m rows, right? This will be m rows, because m summands are there. Always such a partition will have m rows. Now we consider the conjugate partition, and now the first row will correspond to the first column, right? This will be always exactly equal to m, and obviously this is the largest summand in it. So consider the set of partitions of n where there are exactly m summands, and consider the set of partitions of n where the biggest summand is equal to m. There is a one-to-one correspondence between the two, because take a ferrous diagram for one from this partition, set of partitions, where take a partition from the set of partitions where the number of parts are equal to m, and then take the conjugate of that. That will be a partition of n where the biggest part equals m, because the first column will have m things in it. That becomes the first row. That is the biggest part. And conversely, so if you take a partition where of n where the biggest part is equal to m and consider the conjugate of that, it will become a partition of n where the number of parts is exactly equal to m, right, because the row becomes the column here, right. So, you can see that that is a one to one map. It is almost obvious from the picture, let us not waste too much time on that. So, you should verify the bijection carefully, right. So, this is one like from the using the conjugate idea, right, that the fact that given the ferrous diagram of a partition of n. So, and consider if we consider the conjugate of that partition, we will end up with another partition of n. So, and the first look, this is one theorem we can write now, right. Now, let us look at another one. The number of partitions of n plus k into k parts equals the number of partitions of n into at most k parts. So, it is like pk of n plus k, number of partitions of n plus k into exactly k parts. This is equal to number of partitions of n into at most k parts. How do we do that? So, we consider the set of partitions of n plus k first. We will show a bijection to the set of partitions of n into at most k parts. So, if you have a partition of n plus k, say something like this, right. See, now, and it has exactly k parts, that means the number of rows are equal to k. Now, what you can do is we remove one from here, 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 one from here. The last from each row will be, not that in the some of the rows may contain just one, the lowest rows may contain only one. So, we will just remove them like this, right. So, k things are gone. So, the remaining is a ferrous diagram for, this is a ferrous diagram for n, a partition of n. And how many parts will be there? It will never be more than k, it will be at most k, right. So, given a partition of n plus k into exactly k parts, by this transformation we can get a partition of n into at most k parts. Conversely, if you get a partition of n into at most k parts, consider its ferrous diagram, say something like this, right. For instance, you can consider this particular partition. Now, what you can do is you add 1, see add 1 say here at the end of every row. So, clearly it will be a new ferrous diagram which corresponds to correspond to, see for instance, what I do is, suppose this is, see I know that number of rows here is at most k less than equal to k. So, we will add 1 at each of them, but if this was strictly less than k, suppose this many more rows are required to make it k. So, then I will add 1 1 1 here. That means what I am doing is I am adding exactly k new dots to the ferrous diagram. If there are not enough rows, I will have to introduce this single dot rows at in the lowest parts, right. So, total k things will be added. That means we will get a ferrous diagram for n plus k by this operation, right, and it will have exactly k rows in it. It will have exactly k rows in it, and you can see that this is a bijection, because this if this got mapped into this by the reverse operation, we will get back this, right. So therefore, the number of partitions of n plus k into exactly k parts is equal to the number of partitions of n into at most k parts. Now, the next one is a little more non-trivial. Let us look at, so this again we have to introduce what this is about. The number of partitions of n into an even number of unequal parts, distinct parts, number of, that is equal to number of partitions of n into an odd number of unequal parts, unless n has some special form. This is what it says. So, let me introduce what we are looking for now. So, the, say for instance again take the example of 10. The see 10, this is a partition of 10 into just one summand, and they are all distinct. Of course, one summand has to be distinct. So, this is a odd number of parts. There are two properties for this partition: odd number of parts and distinct summands, right. On the other hand, if you consider 10 equal to 9 plus 1, this is again the summands are distinct, but the number of parts is even. So, that goes to the other kind, right. So, 10 equal to 7 plus 1 plus 1 plus 1, this is not even distinct. So, here 1 1 1, these are all same. So, this we do not even consider, right, we are not interested in it. 10 equal to 8 plus 2, this is fine, there are two distinct summands and this will be even number of summands, right. So, you remember when we counted PD of n, we were looking at the partitions of n where the summands are all different. Now, we are grouping them into two categories where the number of, so we are only interested in the partitions which will contribute to this, but then we can put them into two categories, namely those which have an odd number of summands, those which have an even number of summands. We are saying that they happens to be equal in for most n, but it need not be equal in some cases. If n is of the form 3m square minus m by 2, then it will not be equal. One of them will be bigger, that means the number of odd parts, so the number of partitions distinct with distinct parts and odd number of summands can be more than the other type, that means the partitions with distinct summands and having an even number of summands, or the other way, maybe the number of partitions with distinct parts and even number of summands may be more, but whichever is more, it will be more only by 1. The difference between the two numbers will be only 1, that is what I say. And another type of number, for instance, is also this is true, n equal to 3m square plus m by 2. In this case also we can say that they will not be equal, but whichever is bigger, that will be only bigger by 1. So, we can take small examples and see, for instance, see for 1, n equal to 1. So, it is very difficult to try out big examples. So, n equal to 1. So, n equal to 1, so the number of partitions itself, for instance, it is only 1, right, just 1, but this is distinct summand, but then only odd number of summands. So, the first category, so P, D and O, let us say P, D and O, right, that is equal to 1. What about P, D and E? That is equal to 0. This is 1 more than 0. Now, I will say that this n equal to 1 is of the type 3m square minus m by 2. Why? If you put m equal to 1, we will get that is 3 minus 1 by 2 is equal to 1. That's why it is happening. Now we can take n equal to 2. What is happening? Distinct summons, the odd number of them. So the other partition is just 1 plus 1. Right. Here this is not even distinct, so this is not useful. There is only one of them. But then this is again P DO equal to 1 and PDE equal to 0. But I am claiming that n is again of the form 3m square plus m by 2 this time. Why? Because you put m equal to 1, we get 3 plus 1 by 2, that is 4 by 2 is 2. See? And but the difference between PDO and PDE is only 1 here, 0 here. Here also it is 1 and 0, right? But on the other hand, if you go to n equal to 3, now what are the parts? 2 plus 1 and 1 plus 1 plus 1, 3 summons. But then this is not distinct, so we do not have to consider this. So here the distinct summon, this is distinct summon, but this contribute to our PDO because even number of summons, just 1. Here this is odd number of summons, so PDE equal to 1. 1 and 1 equal, right? So you can see that n equal to 3 will not be of the form 3m square minus m by 2 or 3m square plus m by 2. It is not of the form. You can try, for instance, when I put 1 here I got 1, when I put 1 here I got 2. If I get 2 here, that will be 12 minus 2, that is 10 by 2, that is only 5, right? Sorry, 4 into 3, 12 minus 2, that is 10 by 2, 5. Here if I put 12 plus 2 by 2, 7, right? So n equal to 3 is not of that form, right? So but then in that case they are equal. Now we can try with 4, 5, 6, 7, etc. and check whether what we are claiming is correct or not, right? That I leave it to you. In the next class I will continue with a proof of this statement using ferrous diagram. So this is a bit more non-trivial than the proofs we have done earlier. I will continue in the next class.